All right, so today, geometry friends, we're going to talk about section 5.3. We're in chapter 5 and we're going to discuss inequalities in one triangle. And I think after the last two sections, you're going to find this kind of fun. Kind of, hopefully. Let's see if I can get back to the screen we need to be at. There we go. All right, so inequalities in one triangle. This looks like a whole lot of drama, but it's definitely not that big a deal. Here, let's just remember a little bit of the information that we know about inequalities. And so so when we talk about inequalities, it's just a way to compare numbers. And so we know that we can compare numbers and say that, well, A is greater than B, A is less than B, sorry about that. A is equal to B or A is greater than B. Any two numbers are going to have this quality where they're going to fit into one of these categories. So now we're talking about inequalities in terms of properties, but check this out. You remember this from algebra. You remember that if A is less than some value B and then B is less than some value C, clearly A has to be less than C. And similarly, if A is bigger than B and then B is bigger than C, then A has to be bigger than C. So it's a transitive property of inequality, which looks a little bit like the transitive property of equality. The addition properties are the ones that you definitely used in algebra. If you were given an inequality where A is greater than B, if you add the same thing to both sides, that inequality will still be maintained. Similarly, if you have A less than B, if you add the same things to both sides, right, the same thing being C, that inequality will be maintained. Subtraction property is no different. Start off with an inequality, subtract the same things from both sides of the inequality, and what you're going to find is that that inequality, that relationship will remain. So the first theorem that we have is called the exterior angle inequality theorem. And what it tells us is this. And you remember the exterior angle theorem where we had angle 1, like an angle 1, an exterior angle created by the extension of one side of a triangle would be equal to the sum of the two angles on the inside. Well, all this inequality theorem is saying that that one has to be greater than either of those two angles, which totally makes sense because one is equal to the sum of the two angles. So the theorem just basically states if I'm thinking about these two angles here, angle A and angle B, angle 1 must be greater than either of them. All right, fine. Let's see how we can apply that. So here we have example 1. We're going to use this exterior angle inequality theorem. We're asked to find, well, it says use the exterior angle inequality theorem to list all the angles that satisfy this condition. So that measures less than angle 7, has a measurement that's less than angle 7. So let's go ahead and highlight angle 7 so we can keep our eye on it. Angle 7's out here. It's an exterior angle. And I should be able to determine what angles are less than that. Well, first of all, it's an exterior angle of this larger triangle and this smaller triangle. So let's take our time and just pick off the things that we know. The theorem told us that angle 7 is going to be greater than the two remote interior angles. So it's greater than this angle 1, and it's also greater than this angle JKL. So if it's greater than JKL, it's got to be greater than the parts that make JKL, which would be angle 2 and angle 3. So I'm going to list angle 1, angle 2, and angle 3. The next angle I need to look at, or the next triangle, is to observe this one here, this smaller one, triangle MKL. And so what I notice is that this angle 7, is equal to the sum of 5 and 4, honestly. So if it's equal to the sum of 5 and 4, it must be greater than 5, must be greater than angle 5. I'll list that. And it's also greater than angle 4. I'm going to draw your attention to the fact that I changed this to 4 because I think I said that when we were looking at the larger triangle that angle 7 has to be greater than angle 1 and angle JKL, which is 2, 4. And I think I wrote 3. No, I don't think I did write 3. I hope I said 4. So 1, 2, and 4. And then when we look at this triangle, this angle here, and this triangle, it's 5 and 4. And so basically the ones we have are angles 1, angle 2, angle 4, and angle 5. We can definitely say that 7 is greater than those. All right. So what else can we talk about? Can we talk about measures that are greater than 6? So let's turn our attention to angle 6 and let's consider things that are bigger than angle 6. Since our theorem talks about remote interior angles versus exterior angle, I'm going to look at 6 and see if it's a part of a interior angle that can be related to an exterior angle. And I see here's an exterior angle right here. If I look at the larger triangle, and angle 8 is an exterior angle, and remember, exterior angles are always greater than each of the remote interior angles, so I can already say that angle 8 fits the bill. And now if I consider this triangle here, the smaller one, triangle MKL or MLK, right? If I consider this triangle here, look at this angle here, and this angle, angle 3, would be an exterior angle to triangle MLK, and therefore angle 3 would also be listed as one of the angles that we have that are greater, definitely, than our angle 6 here. And I think that's the only one we can say. And I understand the temptation. You're like, obviously 7 has to be greater because we know for a fact that this looks smaller, but that's not what we are allowed to do, because not just because we're trying to use this theorem, but because when you have geometric figures, particularly when you're taking standardized tests, oftentimes it'll say, don't trust what the figure looks like. So you might see something that looks acute, but it might actually be obtuse from the details of the problem. So we can't go around and say, oh, well, clearly 7's bigger because it looks bigger and it's obtuse in this case. And I know that the temptation is there and you want to, because we've been doing it so long. But these are the only two that we can definitely say, given that theorem and given the information that we're given about this particular picture. All right, so now we have theorems 5.9 and 5.10. We're going to talk about angle side relationships, and this is kind of cool. I like it. Basically, what's going to happen here is that if you have a side that's longer than another side, then you know that the angle opposite that side is bigger than the angle opposite the smaller side, which kind of makes sense if you think about like opening something. If you're I think they might do it somewhere in this textbook, talk about like opening a door. So let's say we're looking top down at a door that's being opened. Here's the hinge. If you close the door, right, if you close the door, the opening gets smaller, and so does the angle across from it. And if you open the door even wider, right, the wider you open that door, the wider the angle inside becomes. And so the opening, if I were to measure the opening as a straight line, that larger opening is going to have a larger angle across from it. And so this theorem kind of alludes to that in some sense. So if one side of a triangle is longer than another side, then the angle opposite the longer side has a greater measure than the angle opposite the shorter side. Make sense? So angle here, this guy, angle Z, is going to be greater than angle X. And then the converse, kind of like the opposite of it, is talking about angles leading to sides. So if one angle of a triangle is greater in measure than another angle, then the opposite side of the greater angle is longer than the opposite side of the lesser angle. This being 110 degrees tells me that KL is longer than JL, because JL is opposite a 45-degree angle. Specifically, honestly, I can tell you that KL is the longest side of the triangle, because there's no way that this angle could be as large or larger than 110, right? All right. So let's look at an example that will help us to deal with that idea. So list the angles of PQR in order from smallest to largest. So we can take our Q from that last theorem, circle the smallest side, and now we draw an arrow to the smallest angle. So from smallest to largest would be angle Q first. And then we'll take our next largest side, which is PQ, and opposite that is R. So the next largest angle is R. And finally, the largest side is 9.1, or RQ, which has opposite it, couldn't really draw that, angle P. And so this, not angle B, Dion, angle P. All right. So this would be the order from smallest to largest. In example 2, we're going to list the sides that of from shortest to longest. And the beautiful thing about having two angles of a triangle, we automatically know the third angle, right? So if this is 45 and this is 56, I can calculate that this remaining angle is 79 by taking 180 degrees and subtracting the sum of these other two angles. So now that I've got that this is 79 degrees, now I totally can tell you the shortest to the longest. So the shortest side is going to be opposite the 45-degree angle, and that's going to be FH, segment FH. The next shortest side is going to be GF. And the longest side, or the largest side, is going to be segment GH. And so that's how we can apply that theorem. That's not too bad. All right, so here's our real world example. All right, so angle side relationships. Let's just see if we can find the math in this business. An interior designer uses triangulation to create a depth in a client's living room. If the measurement of angle B is to be less than the measurement of angle A, which distance should be longer, the distance between the two lamps or the distance from lamp B to the midpoint at the top of the artwork? And we're to explain. We'll just discuss. All right, so let's go back. We know that the measure of angle B is to be smaller than the measure of angle A. And so the question is, which distance should be longer? The distance between the two lamps, that's from here to here. So should BC be longer, or the distance between the two lamps, or the distance from lamp B to the midpoint? Or should this be longer, or BA? So which one should be longer? Well, if this is increased, we know that this angle increases. And if BA increases, what that does is that increases C and doesn't necessarily have a desired effect on B. So it would make sense that if we can increase the distance between the two lamps, we would effectively make this the largest angle, therefore ensuring that B is less than the measure of angle A. I think that's all I got to say about that. Hopefully that makes sense, guys. And it looks like we have reached the end of our lesson. I kind of like this rule. The examples that you should have in your on your worksheet should be pretty straightforward and simple. I would expect that you can get through this section 5.3 with relative ease. But if not, that's okay. Let me know and we can talk about it. I look forward to talking to you guys soon. Take care. Bye-bye.